continuation of the 10-week Columbia Mathrani program that we've been running in the department this summer. We're pleased to start off with Jason Behrstock's group. They were led by Jason, Shin, and Daniel. And so we'll have Sarba, Lena, Robert, Samir, and Ayam talking about the geometry of Coxeter groups.
All right, good morning, everyone. I'm Samir. This is Robbie, Lena, Ayang, and Sarba. As Professor just said, we were in Professor Jason's group, and we worked on the geometry of Coxeter groups this summer. So I'm going to start off by, or Lena and I are going to start off with some background material. I'm going to talk about what a Coxeter group is, and then we're going to introduce some notions of thickness and divergence, which we studied a lot this summer. Robbie is then going to talk about some algorithms that he worked on to determine upper bounds on thickness, and then finally Sarba and Hayang are going to talk about random graphs and what happens at constant probability densities. So I'm going to start off by defining a right-angled Coxeter group. So given any finite simplicial graph, say gamma, the right-angled Coxeter group associated with it is the group where the vertices of gamma correspond to generators in the group. Each of the generators has order 2, and an edge between two vertices of generators signifies a commutative relationship, and obviously the absence of an edge signifies no relationship. So these are some examples. So we have the infinite dihedral group there. So you have 2 generators and there's no relationship between them. So you sort of can get these infinite word lengths. So if you have 2 generators A and B, since there's no relationship between them, you can sort of start getting A, B, and you could sort of have these infinite words. Similarly, if you look at this, which is got 2 generators and they commute with each other, you get nothing but the Klein-4 group. And then this is just a direct product of 2 of these same infinite dihedral groups. So these are just some basic examples of right-angled Coxeter groups. I am now going to let Lena talk a little bit about the Davis complex and divergence, and then I'll come back and tell you guys a little bit about thickness.
So if you have a graph and you have the Coxeter group associated with it, there's a cube complex associated to that Coxeter group, and it's called the Davis complex. How you build it up is essentially the one skeleton is the Cayley graph corresponding to that group. The Cayley graph is just a presentation of a group where from each vertex we have essentially edges coming out of it corresponding to the generators of the group. And then to build the rest of the Davis complex for each complete subgraph on n vertices in the graph, you have a corresponding N2. So for example, if you have an edge connecting 2 vertices, then you get a square in the Davis complex and so on. Next we'll define divergence. What divergence basically is a growth function that describes the avoidant path in a space. For example, for example in R2, if you want to take a ball of some given radius and you want to cut it out of a point, the divergence will describe the length of that avoidant path to avoid that ball. So I guess in R2, the divergence would be linear because the equation for the circumference of a circle is just 2 pi r. So here's an example of a Cayley graph of a Coxeter group. It's one from earlier, 2 slides ago. So this is just the infinity cross the infinity. The Cayley graph associated with this is quasi-isometric to R2. If you build the Davis complex out of this, it just looks like basically a grid of squares that goes on forever. So this has linear divergence because it's just R2. So here's another example of a graph. This is just a pentagon. The Cayley graph corresponding with this pentagon is as you can see is the picture on the right. So from each vertex you have 5 edges coming out, corresponding with the 5 vertices which generate the Coxeter group for the pentagon, and as you can see, the divergence in this case is not linear. So in particular, the type of divergence in these kind of spaces is hyperbolic, which basically means that the divergence is bounded by an exponential function. So here's some picture by MC Escher, which also shows exponential divergence. So as you can see, as you increase the radius of the ball, the number of, I guess, angels or demons that you have to pass through increases exponentially. So in context of the Coxeter groups that we were working with, we want to use divergence to study a geometric invariant called thickness. Basically, what thickness of order 0 in a group corresponds to linear divergence, and thickness of order 1 corresponds to quadratic divergence, and so on. So one way we can use to get a lower bound on thickness in Coxeter groups is to find the divergence in the space corresponding.
So I guess Lena gave us sort of an idea of how to understand thickness through divergence, and I'm sort of going to give a slightly different notion of thickness. So if you look at any finitely generated group G, we say that it's algebraically thick of order at most n if we can find this collection script H of quasi-isometrically embedded subgroups that satisfy certain conditions. So effectively what we want is that if we take the union of all these H in script H, we generate the entire group G or some finite index subgroup of it. Then we want each of the quasi-isometrically embedded subgroups to be themselves thick of order at most n minus 1. And then finally, if you take any two of the quasi-isometrically embedded subgroups, H and H prime, we want to have this sort of sequence of HIs such that the intersection of any two consecutive ones is of finite order, or sorry, infinite order, excuse me. So that's sort of a slightly different characterization of what thickness is, and so that gives us sort of an upper bound of things that we know that something is thick of order at most n. And if we also at the same time know that it's not thick of order at most n minus 1, that's sort of how we can get a precise bound or get a precise order of thickness. So I think this is sort of what we worked on a lot this summer. And so sort of to start off, I'm going to talk about a couple of basic algorithms that we used and then implemented both using Python and C++ to get exact thickness for thickness of order 0, and then I'm going to talk about thickness of order 1. So we have this theorem that thickness of order 0, which is, as Lena said, basically having linear divergence, is equivalent to being a direct product of two infinite subgroups, or that's equivalent to the graph basically being a join, and join with, as long as it's not a join with a clique. But effectively, the problem boils down to checking whether a graph is a join. So this is sort of a very basic algorithm that it's just to check whether two graphs or whether a graph is a join, and we implemented this. So effectively what you're trying to do is you start with the vertex, and then you keep track of all other vertices that must be in the same join component. So if you have a vertex, every other vertex that's not connected to it must be in the same join component. So you start with a vertex V, and you add it to this list L. And then you keep adding all these other vertices that must be in the same join component. So it starts with all the vertices that are not connected to V, and then you keep going. So now you have, let's say you have 5 new vertices there, you check each of those and add all the vertices that are not connected to those. So you're sort of building up this one join component, and you're using the logic that it's in the same join component for sure if it's not connected. And so you sort of build up this list L, and then finally when you can no longer add vertices to L, you look at L and you say, okay, if now I have all the vertices that have been added to L, they're all in the same join component, and therefore the graph is not really a join. They had to be in the same component. Whereas if you have just a subset of the vertices in L, you know that your graph was a join, where that's one component and the remainder are another component. So this is sort of a basic algorithm to look at whether a graph is thick of order 0. And similarly, there was this condition known as the CFS condition, which stands for a component full support, that came from a paper by Donnie and Thomas that we sort of used and again implemented using both Python and C++ with various different implementations. And sort of the idea behind this is you look at the graph gamma of the Coxeter group, and you generate a new graph which is known as gamma 4. And it's basically what's called the associated 4-cycle graph, which basically you take all the 4 cycles in gamma. So you look at all the squares in gamma, and each of those become vertices in gamma 4. And you connect 2 of these vertices in gamma 4 if the 2 squares in gamma shared 2 edges or shared 3 vertices. So that's sort of, you're looking at these squares, and then you generate this graph based on overlapping squares. And then finally, what you do is you look at this graph and you try and find a component of the graph which is a connected component and what's known as it has full support. So what that means is that the component gamma 4, if you look at that component and then the associated vertices back in gamma, you cover all of gamma. So you have a connected component in gamma 4 and then the associated vertices give you all of gamma. And that's sort of what's known as the component with full support. And that's sort of tells you whether, and then you also obviously make sure it's not a join, so it's not thick of order 0, and therefore it's thick of order 1. So that's sort of what we spend a lot of time on, or at least I spent a lot of time on this and implementing this. And then I guess Lena's going to talk about some examples, and then after that Robbie will actually talk about algorithms for higher orders of thickness, or at least getting upper bounds for other things. So okay, Lena.
So this type of graph also comes from the same paper by Donnie and Thomas. In this paper, they found like a specific class of graphs where they can get a sharp upper and lower bound on the order of thickness. So they basically did this inductively. They started building up from a square, which is thick of order 0 because it's a join, and then they added like specific edges and vertices to see what happens. So for this type of graph, the thickness is bounded by, or the thickness is order d minus 1 because the divergence is r to the d. So for this particular one, starting with this would be labeled B0, so this would be thick of order 5. So what we were working on, one of the things was to try to understand and modify the argument and see if we could generalize it and apply it to other graphs. So for example, if you add this edge on the bottom, this reduces the divergence from order 6 to order 5. So the order of thickness goes down by 1. It's because you can see there's this subgraph inside it which has a thickness that we know. Note that this is not always true. This just happens because for the specific graph, if you go into the Davis complex, you can sort of force any path in the larger graph to go through this specific subgraph. But one of the things we're still working on is how to generalize and apply that arguments to other situations. So I think, sorry. Yeah, so this is one of the, so this is another one of the graphs that we were looking at. For this one, we can get an upper bound and a lower bound on thickness, but it's not exact. So we're working on sharpening that and trying to get something a little more precisely.
Thank you. So at the start of the summer, we have this theorem by Behrstock, Hagen, and Susse, which says that W gamma is thick of some order if and only if gamma can be formed by taking thick unions and coning. So what does that mean? So if you start with two graphs, this one and this one, both of these are going to be thick of order 0 because they're joins. This is a join between like the vertical vertices sort of and the horizontal vertices. Likewise for this one. You could take their thick union. So they're thick graphs, and if they share a subgraph, which we'll say that this square, and that square is obviously not a clique because it's missing, for example, this edge and this edge. A graph gamma formed by taking both of them together and arbitrarily any edges between, for example, you could connect this vertex and this vertex because they're not in an overlap. The graph that you get, which is like this, is called a thick union of both of those graphs. And to prove that it's thick, you can take each of these subgraphs to correspond to your subgroups. And the requirement that their overlap is not a clique ensures that their intersection is infinite. You can also cone. So if gamma is a thick graph with a subgraph lambda, which is not a clique, and lambda here is going to be this vertex and this vertex, the graph gamma prime formed by adding a new vertex v, say this one, and an edge between v and every vertex is lambda, so here and here, we say that gamma prime, this new graph, is formed by coning off lambda. And this turns out to be actually one of, or really close to one of the Donnie-Thomas graphs, so that's how those are formed. And that's also, I guess, another proof of why they're thick of some root. So a theorem that I proved is that coning, you can cone off not just one vertex, but you can cone off an entire clip. For example, this is a little triangle. And you only go up thickness by order at most 1. So if gamma naught, which is this little circly thing, is a graph whose corresponding right-angled Coxeter group is thick of some order n, and lambda is a clique with k vertices, and each of them is coned off on some diameter 2, i.e. not complete or not clique subgraph, then the resulting graph gamma corresponds to a group that is thick of order at most n plus 1. And it turns out that the collection that demonstrates this is the set of conjugates of the original graph W gamma by all combinations possibly of any generator in lambda. So if you have k vertices, that'll be 2 to the k combinations, including, as you can see, the one with none. And the really interesting part of this proof is to show that you can get a finite index subgraph or finite index subgroup, of the entire new graph. And what you do is you find a homomorphism phi from W gamma to Z and Z to the K, or Z to Z, to the K, Z1 to Z. And in fact, the kernel of this homomorphism is any word that has an even number of the generators that are in this clique. And it turns out that the condition that you have an even number of them is precisely what you need to ensure that it can be built out of these conjugates. So applying what we know from here, and similarly you can also show that you can take any number of unions at one step at once, as long as they each intersect. So applying both of these, we get two algorithms that can give you an upper bound on thickness. The first one, you alternate unions and cones. So you start out actually by building a script M, which is a collection of maximal thick joined subgroups, or subgraphs rather. So for this graph in particular, the maximum joined subgroups that are that are thick are going to be these two. And you start out with thickness T equals 0. And then in alternating unions and cones, you first check whether gamma is in script M. For this graph, it's not. And then next, you take unions across script M so that in the result, you get every n in script M is thick of order at most T plus 1. So in here, it would be you take the union of these two, and you get everything but this vertex over here. So then you check whether M changed. If yes, then you say, well, we've gone up at least, or at most, one more order of thickness. And you check if gamma's in M again. And again, here it's not. So here you would check, you would then code in the biggest possible clique, which is actually just this vertex, to each n in M, so that each n in M is thick of order at most, again, T plus 1. And you check whether M changed. Again, it did. So then we say that T then goes up by 1, and you repeat from step 1, where here we would check whether gamma is in M, and in fact it is. So this first algorithm tells us that our upper bound is 2 for this graph. And you continue going. If you happen to not change M twice, then you report failure, if you don't have gamma in M. Another algorithm that I wrote, thinking that it would actually give a lower number, because it seems like you can get more from taking a bunch of unions at once rather than doing a bunch of coning, is you take unions until you can't anymore, and then code. And in fact, both the algorithms coincide for this graph to both give 2. It turns out to be that neither algorithm is optimal. For example, sometimes they'll give 2 when the answer is actually 1. But and neither of them consistently gives a lower number than the other. In fact, the unions one, or I thought the unions one would always, but I found a graph that gives, this one gives 45, and this one gives 50. However, in practice, they've been surprisingly effective, and they've allowed us to graph things. So here is a movie that we made. And what it shows you is as the density of a given number of random graphs that we've generated increases, you sort of see how the program estimates thickness over time. Surprisingly, as you increase either the number of vertices or the density to a certain regime, you get thickness of order 1 almost always. Also, interestingly, the program slows way down. I wrote it in Haskell, but it slows way down when the answer is going to be 1. Trying to go to the next slide. There we go. Oh. So another thing that we did was had the program sort of stop once 10%, 50%, and 90% of the graphs that I was finding on, I think, before we were using 50 graph samples, and here we're using 10. So stop when 10%, 50%, and 90%, where it's like order 1. And you can see as the density decreases, the number of vertices needed to get to these regimes increases, it seems, super linearly. And I'll turn it over to Sarba and Hayam.
So I'll be talking about random graphs. Hayam and I worked on basically generalizing a result that was previously proven. And I'll start by talking about the construction of your random graph application. So basically, to construct a random graph, what we do is we first fix a number of vertices. So say we have 4 vertices, and then for every possible edge, we assign a probability that we have. And this is the model by addition, Rennie. So the important things here are that this graph is, first of all, simple, and secondly, undirected. Undirected means that the edges don't have directions. And secondly, simple means that there's at most one edge between 2 vertices, and there are no self-loops. And while constructing this graph, the way we do it is we fix a certain probability p for every edge. And the p is sort of constant in the sense that the probability of having an edge between these 2 vertices is the same as the probability of having an edge between these 2. Or any other edge for that matter. So we're not doing something like this edge is probability p and this one like p to the n or something like that. It's all the constant probability. And secondly, this p is independent of the number of edges. So just because there are 2 edges here does not mean that the probability of a 3rd edge would decrease or increase for that matter. And the second concept we require is something called asymptotically almost surely. So we're investigating thickness of random graphs, and the way we look at thickness is through a concept called asymptotically almost surely thick. So first I'll define what almost surely means. If we take any sample space and want to see the probability of an event occurring, almost surely just means that it will occur outside a set of measure 0, which, for example, is say we have a line which covers both ends. So if we remove a few points here and there, the probability of selecting something from the line would still be 1, but it would be almost surely 1 because we may not get those points, but the probability of getting any of those points would be 0. And asymptotically almost surely means that we're getting a result almost surely, but as I mentioned, we fix the number of vertices n, but now we let that n go to infinity. So that's the asymptotic part of the asymptotically almost surely. The result I was talking about thickness is here. This is a paper by our professor and 2 other professors, Mark Hagen and Alessandro Sista, where they prove that at constant probability half, the graph is asymptotically almost surely thick, and we're looking to generalize these results for other probabilities. I'll hand it over to Hayam.
So the reason that p equals a half is an easy probability to use in proving this is that a half equals 1 minus a half. So when you take the binomial distribution, a lot of these things simplify, and it gets rid of the need for a lot of extra factors that we had to introduce. So this is the so me and Sarba tried to generalize the result to a more general P, and we proved it for. So we couldn't prove it for all P, but we proved it for this range. You should ignore that E cubed thing. It's not right, but and so the proof to prove this, we took the original proof in our professor's paper, which is about like 4 pages long. And so this limit here, so we first set some upper bounds for pi of 2n and pi of n plus 1. And we have this function f of n, or fp of n, and we prove that it's summable. And using those 3 results, we get, if you call this number alpha, in the end we need to prove that f of 18 will be less than or equal to alpha minus alpha squared. So this is alpha minus alpha squared for various probabilities, various numbers of vertices. So 9 took like a couple of, so what the data this is using is the number of thick graphs, the total number of thick graphs on n vertices, and also the total number of clicks in those thick graphs. So for 9, that took about 2 days to compute. For 10, it would be inconceivably long time. So we use 9, and you see here that for above about 0.48, this number is greater than 0. Below that, it's less than 0, so it's not really of any value. And so the range we proved it for was most of this range. That's about 0.493, and that's 0.96 something. So since that's greater than 0, we prove that it is asymptotically or Wilshire thick for those values of P.
That's everything.
Yeah. So yeah, I guess. So yeah, thanks for listening. We just want to take this opportunity to thank our professor, Professor Behrstock, and our TAs, Tim and Dan, and also thanks to the RU program for making this all possible. So thank you.
Are there any questions for Jason's work?
Can you compute the thickness of any other groups besides Coxeter groups?
Yes, or we began by studying it for right-angled arc groups. And in fact, I think every right-angled arc group is either hyperbolic or it's like it's order 0 or 1, which is why Coxeter is sort of interesting, because that's not the case for them.
Thanks for
Thank you.
again.